In this video, we're going to be talking about series and convergence. And we're going to start talking about convergence and divergence of some series. And it'll give us our first few series and whether or not they converge or diverge. It's a fun, exciting topic. Okay, so an infinite series is an expression in this form where you have your first term, second term, so you have a sequence that all sums up and gets you to a series, but you're going to infinity. Okay, a partial sum is the sum of the first few terms of that series. And then a series is said to converge if you can actually find that sum. Series is said to diverge if there is no sum. Okay, so our first example here. And we want to find a sequence of the partial sums. So I want to find my first partial sum. So basically, if I were to plug in 1 for n, so that is 2 over 3 squared, which is 9. My second partial sum is I take my first partial sum, so I take my first term, I add it to the second term, so that's going to be 2 over 27. And you get 8 over 27. Your third, you take 2/9, you take 2 over 27, and you add to that 2 over 81. And we get our sum is 26 over 81. Now I have a little note here in the bottom. The book says that the sum of the nth term is 3n minus 1 over 3 to the n plus 1. And I'm not going to lie, guys, I have no idea how they got that. So I kind of challenge you. If you could explain to me how you got that, how they got that formula, that would be great. I bet you it probably has something to do with this is my third partial sum when the bottom is 3 to the n plus 1. So notice how my denominator was always the same thing. They were looking at a pattern that I didn't see. And then this is 3 to the n minus 1. This is 3 squared minus 1, 3 to the third minus 1. That's how they got it. They were just looking at the pattern. Okay, so I lied. I'm not going to give you any extra credit. I went through, I figured it out, I thought about it. But that's what I love about math. And I'm going to go on a little tangent here in the middle of a video, I'm sorry, is I love that sense of accomplishment. Once I finally figure something out. And I finally realized, oh, that's how they got that. It's a big sense of accomplishment. So I'm going to go and I'm going to feel like my sense of accomplishment today. Okay, let's find the sum of this series. And there's a trick to this one. The trick to this one is, I kind of have a hint over here. It's a telescoping series. Telescoping series are not on the AP test, but I just love them. I think they're really, really, really cool. And what you have to do is you have to break this down into partial fractions. And it wasn't until technically it was 2020, I was scared of telescoping series. But they're not that bad. Okay? Breaking this down using partial fraction decomposition, we get this. Okay. So now let's start plugging in numbers. If I plug in 1, we get 1/2 minus 1/5. And I'm going to add that. So if I plug in 2, I get 1/5 minus 1/8. If I plug in 3, I get 1/8 minus 1/11. Hopefully you see a fun pattern showing that this last term and the first term all end up being the same. So as I move through my infinite series, I have 1 over 3n minus 1 minus 1 over 3n plus 2. So remember, I'll X these out. Those cancel. Those cancel. Those cancel. This one cancels with one that's there that I didn't write. One that's sitting in here that I didn't write cancels with this. So this actually turns into this sum. And we're looking as n goes to infinity of that sum. That whole sum there is going to equal 1/2. So that's just an introduction into telescoping series. I think they're kind of fun because the middle terms all cancel and you have the first term, you have the last term, and they're going to simplify. Again, not on the AP test, but I really think it's something fun for me to throw at you guys. Okay, geometric series. This should hopefully look familiar from Algebra 2 and pre-calculus. And it's a good review. So geometric series, you have a common ratio. You have some common ratio that you're going to have. Okay, and then you converge if the absolute value of that ratio is less than or equal, or less than 1, not equal to, less than 1, and this is going to be the formula for that. Okay, it diverges if your ratio is greater than or equal to 1. And the interval of convergence is said to be -1 to 1. So when your ratio is -1 to 1, that's going to be the interval of convergence. The ratios where you converge. Okay, my ratios of a geometric converge if I'm between -1 and 1. So let's look at some geometric sequences, or series, I apologize, series. So you want to look for what's the ratio. You want to look for what the exponent is. So here, and if you want to write out a few terms, you can write out a few terms. I would have 3/5 plus 9/25 plus 27 over 125, and I keep going on forever. My ratio is 3/5. My ratio is less than 1, so we converge. So let's find that sum. I find that sum by taking my first term, which was 3/5, over 1 minus my ratio, which just also happened to be 3/5, and that simplifies to 3/2, and that's what my ratio converges to. Let's look at this series. We have pi over 2 minus pi over 2 squared plus pi over 2 to the third plus So hopefully you notice I go minus plus. Technically this one would be minus. I should maybe change that to a minus. So my ratio here is negative pi over 2. And I need to determine if that is greater than or equal to 1. It is greater than 1. So therefore this diverges. I knew this because pi was 3.14. 3.14 divided by 2. I know it's going to be greater than 1. Okay, now we're interval of convergence. So the interval of convergence of a function, we're going to be finding this a lot. It is really helpful if you recognize geometric series when we have interval of convergence. Okay, so this is a geometric series. I know it's geometric because I have this something to the nth power and there's no other n's anywhere else. Okay, so the interval of convergence, remember, -1 less than 1, where what goes in the middle here is your ratio. If I multiply both sides by 2, and then I subtract 3, Okay. Yes. So for x's within this interval, so if I plugged in negative 2 there, yeah, wait, so if I multiply, yep, I did all that math right. I don't know why. So if I plug in any number x that's on this interval, I should be able to get a ratio where I'm going to have a geometric series that will converge. Okay, we have our first test for convergence, or technically this is a test for divergence. And I want to highlight something with you here. This is a test for divergence. This does not prove convergence of series. Okay, so if you have the limit as n goes to infinity of the function that you have inside your summation formula does not equal 0 or fails to exist, then you diverge, okay? Again, this doesn't prove convergence, it only proves divergence. So this example here, use the nth term test for divergence to determine whether each diverges. So I find the limit as n goes to infinity of our function. So I look at this and I notice that the top is going to get bigger than the bottom. So this is going to go to infinity or does not exist. So therefore this series diverges. I won't be able to find a sum. For part B, limit as n goes to infinity of 2 over n plus 1. Well, that equals 0. So this test is inconclusive. Okay, it does not necessarily prove that it converges. I'm going to be giving you guys a whole bunch of more tests that are going to prove whether this converges or diverges. Okay, but just worry about our nth term tests. We're building our basket of tests. And then here on this one, the limit as n goes to infinity of n cubed over 7n cubed plus 2. So this limit ends up equaling, I don't know why I have 1/3 in here. Powers are the same, it equals 1/7. I don't know why I have 1/3 in my notes. I don't know what I was thinking. So since this doesn't equal 0 or fails to exist, then this diverges. I don't know why. I struggle with the nth term test. I don't know why I've always struggled with that. And of all the tests, it's the easiest of the tests. I don't know why I always struggle with remembering what the nth term test is. Okay, this last example I threw in here because I think it's a good example of geometric series. I think it's a fun example of a geometric series. So a ball is dropped from a height of 4 feet and begins bouncing. The height of each bounce is 2/3 the height of the previous bounce. Find the total vertical distance traveled by the ball. Okay, so let's draw a little picture of what's happening here. So a ball is dropped from 4 feet. And it bounces and it retains 2/3 of that. So bounces, comes back up. This is 2/3 of 4, so that's 8/3, and goes back down as 8/3. And then I come back up and another 2/3. So another 2/3 would be 16/9. And so on, and so on, and so on, and so on. So our first distance that we traveled was 4. Traveled 4 down. Our next distance, we traveled 4 times 2/3 up plus 4 times 2/3 down, and that becomes 8 times 2/3. Our third distance, so this third bounce, is 4 times 2/3 to the third power, I'm sorry, to the second power, plus 4 times 2/3 to the second power, because I have one 2/3 and then a second 2/3. So that becomes 8 2/3 squared. Hopefully you see that the next one would be 8 2/3 to the third. So what we have here is we have a series. We have our initial 4, our initial bounce, plus 8 times our series we know that this is geometric, okay? And so I have 4 plus 8 times by my summation formula. And when I simplify all of that, we get 20 feet. So that is the wonderful and exciting world of, what do we cover? Nth term test for divergence and series and convergence and our geometric series. We talked about a telescoping series. So that was a fun day and starting our infinite series. Thank you for watching.